Hi, welcome to L4M. In this video, we will finally start to talk about proof by contradiction method. In the first three videos, plane geometry 6.1, 6.2, and 6.3, we learned about propositions, truth values of propositions, negation of a proposition, conditional clauses, truth values of conditional clauses, some real world examples about conditional clauses, negation of a conditional clause. They were all to create a base knowledge to understand proof by contradiction. So we can start now to talk about proof by contradiction. Before proof by contradiction, I want to quickly go over direct proof. In math or geometry, there are some methods we use to prove theorems. I will not go over all proof methods, but for example, to prove a conditional clause, which is a proposition having the form if P then Q, that's the conditional clause, right? If P then Q, we frequently use the method called direct proof. In direct proof, we think about the case when the condition P is satisfied, and we try to show that consequent Q follows. So in other words, we assume that P is true and we try to show that Q is true. That's the direct proof. But in some proof methods, we don't follow this method. We don't follow this way. We don't start from P and reach Q. We use some other ways. Those are called indirect proof methods. So proof by contradiction is a kind of indirect method of proof. We sometimes use not direct proof ways, but some indirect methods of proof to prove our theorems. One of them is proof by contradiction. There are some other kinds of indirect proof methods except proof by contradiction, but we will not talk about them because we just focus on proof by contradiction in this video. Okay, what's the idea of proof by contradiction? Sometimes it's easier to prove that the negation of a proposition is false rather than proving that the proposition is true. This is the idea of proof by contradiction. So, proving that negation of R is false means that we actually prove that R is true. So in proof by contradiction, we try to show that negation of R is false instead of proving R is true, because this one is easier. Because we know that if negation of R is false, this means that R is true once more. Okay, now remember negation of a conditional clause. Negation of a conditional clause. Let R be the conditional clause if P then Q, then the negation of R is P and not Q, right? When we use the proof by contradiction method, instead of proving R is true, we try to prove that negation of R is false. We try to prove that negation of R is false. Okay, so how do we do it by proof by contradiction method? First, we actually have three simple steps. In our first step, we assume that negation of R is true. Okay, what we need to prove is negation of R is false, but in the beginning we just assume that negation of R is true. Remember, negation of R, it's P and not Q. So we assume that P and not Q is true. In other words, we assume that P is true, but Q is false. Okay, P is true and Q is false. And we assume that negation of R is true just to get a contradiction later. for a future contradiction. Okay, we assume this, we make this assumption for a contradiction. What does a contradiction mean? We will see it in a few seconds. Okay, so we start with the assumption that negation of R is true. And then, while working under this assumption to prove our theorem, we arrive at a contradiction. We reach to a step where we see a contradiction. So contradiction is something which is logically impossible. Or contradiction is something that conflicts to a known fact, or that conflicts to a known axiom. What may be this fact? It may be an axiom, or it may be a theorem which we have previously proven, and we know that it's true. So we assume that negation of R is true, but we arrive at contradiction. This means that our assumption about negation of R is false. So negation of R cannot be true because this leads me to a contradiction. At this point, we understand that negation of R is false. So this means we prove that negation of R is false. And since negation of R is false, we conclude that R must be true. So if P, then Q must be true. Okay, this is the main idea of proof by contradiction. Assume that negation of R is true, then find a contradiction and understand that this assumption must be wrong and negation of R must be false, which means that R must be true. Okay, if you remember in lesson video 5, I mean plane geometry 5, in that video, we saw theorem 2 and we proved this theorem using proof by contradiction method. This was the first time we saw proof by contradiction method. That's why I started to create these 4 videos about proof by contradiction. So let's see this theorem, review this theorem once more, and go over the proof to understand it better, to make it more clear. Theorem 2 says, two lines which are both perpendicular to a third line do not intersect. So I don't see a conditional clause here, but I can rewrite the theorem number 2 and I can write it as a conditional clause. So let R be the conditional clause now, which expresses the same meaning as theorem number 2. If two lines are both perpendicular to a third line, then these two lines do not intersect. So if two lines are both perpendicular to a third line, then these two lines do not intersect. If I say that this part is my P and this underlined part is my Q, then the proposition R becomes if P then Q, where P is two lines are both perpendicular to a third line and Q is these two lines do not intersect. Remember that in proof by contradiction method, we assume that negation of R is true, which means we assume that P and not Q. So we know P and Q. So if Q is these two lines do not intersect, what is not Q, which means negation of Q? Negation of Q means these lines do intersect. So we will assume that P is true and negation of Q is true. Okay. So to prove this theorem, first we assume that we have two lines that are both perpendicular to a third line. We assume that these two lines are intersecting. Okay. Okay, here is our proof. Assume that negation of R is true, which means assume that P is true and we have two lines that are both perpendicular to a third line. Let's say that those two lines are A and B and they are both perpendicular to a third line, C. And we also assume that Q is false, or negation of Q is true, which means that these two lines A and B do intersect. They are two intersecting lines. Okay. Now we start to work under this assumption. Now we have line A, line B that are both perpendicular to the line C here. This is the line C. And we assume that these two lines intersect. Now, how do they intersect? Of course, on this figure, it's a little weird to show that these two lines are intersecting. They are actually not intersecting, but under our assumption, I must assume that they are intersecting. Let's say that line A and line B are intersecting at a point like Q here, okay? Q1, let's say. Okay, so Q1 is a point on A, and Q1 is also a point on B, because it's the intersection point of these two lines. Okay, now if you assume that this figure is on a paper, on a flat paper, and if you fold this paper along the line C, for example, any point on line A here, like A1, will fall onto a point like A2 here, right? And similarly, any point on line B, like point B1 here, will fall onto a point like B2 here. So B1 is above line C, B2 is below the line C, and similar idea for A1 and A2. When we fold the paper, for example, along this line C, B1 will fall onto B2 and A1 will fall onto A2. And this will happen for any point on the line A above C, and for any point on the line B above the line C. So when you choose any point here, it will fall onto another point there. So this will happen for the point Q1 as well. So Q1 is a point on A, so when I fold the paper, Q1 will fall onto a point like Q2 here. So since Q1 is on A, Q2 should be also on A, which means that A is a line which is passing through point Q2, right? I'm repeating, this is a little weird. Of course, line cannot go like that. Line must be straight. But since I assume that lines are intersecting at Q1, so Q1 will fall onto a point like Q2 here, which is also on the line A, because Q1 is on A. Similarly, Q1 is a point on B. That's why when I fold the paper, the point on which it falls, that's Q2, it must be also on the line B at the same time. So line B also passes through the point Q2. So I see that A and B are both passing through Q1 and Q2. So these two lines are intersecting at 2 points, right? We know that two different lines cannot intersect at 2 points. Two different lines are either parallel or they intersect at only 1 point, for example. This is a contradiction. Another contradiction is, remember axiom number 1, that was in our first video, plane geometry video number 1. Axiom number 1 says that through 2 points in the plane pass a line, and that line is unique. So through point Q1 and Q2, we have only one single line passing through these 2 points. But I see two different lines, A and B, passing through the same 2 points, Q1 and Q2. That's a contradiction. This contradicts to a known fact. That's our axiom number 1. That's why it means that our assumption here is false. So negation of R cannot be true. Negation of R must be false. So because of this contradiction, negation of R is false, which means that R is true. Remember what R was? R was if P then Q. So R was if we have two lines that are both perpendicular to a third line, then these two lines do not intersect. That's true then, right? So that's the idea of proof by contradiction. I hope that it makes more sense now. Stay with us, subscribe our channel, and see you in next videos. Thank you. Stay with us. Bye.